Hey everyone, we're gonna get started. So if anybody is near the bar or the windows, feel free to take a seat. Thanks everybody for coming to this meetup. Your previous organizer, Nick, has left New York, unfortunately, and I have taken over the organization of this meetup. So now I can be your point of contact if you know anybody that wants to speak at this event, or even people who you know are good presenters, let me know, and I'll work on convincing them to come present here about Go or anything related to Go. Today we have two presenters. First one will be Adam Glassman, and he's going to be presenting about how to create DSL-style things with Go. And we'll start there, about 30 minutes, and then another presenter will come on for the last 30 minutes. And I'll leave it up to you now.
Testing, 1, 2. All right, hi everybody, happy spring. My name's Adam. I work at AQR. I actually work mostly in Python these days, but Go is very near and dear to my heart. So pretty happy to be here today talking about Go syntax tricks for DSLs. So DSLs, of course, being domain-specific languages, which in this day and age has come to mean something like a language within a language. It's an API that exists within another language that is written in such a way as to look a little bit like a language unto itself. And typically it works in something of a declarative style. Declarative as opposed to imperative. Imperative being if you were to walk into a pizza place and say, hey, roll out some dough, sprinkle some cheese and some sauce, and put it in the oven. If you went into a pizza place in New York City, you would deserve the types of looks you would get if you said something like that. More commonly, we describe what we want and we get it. We say, give me a cheese pizza. So DSLs describe what we want to build, what we want to assemble, rather than the steps that we're going to go through to assemble it. And so constructs like that have become really common in languages like Ruby, where there's a lot of magic. They have a very forgiving syntax. There's a lot of features that are very different from what we've come to associate with Go. Some pretty well-known examples are Chef, the configuration management tool, Rake, which is sort of like a build task tool, Active Record. What I have up on the screen right now is a DSL for working with Solar, which is a text search engine. And you can see rather than imperatively assigning a bunch of variables, going through a bunch of steps, filtering the output, it's sort of a description of a query that we might execute, and then we count on some magic under the hood to do the thing that we've described. And so something like this relies, as I said, on a very flexible, squishy syntax, and a lot of magic under the hood, like a lot of crazy method resolution rules and other metaprogramming tricks. And again, those are things that we have been explicitly left out of Go. In my last job, I worked half the time in Ruby, half the time in Go, and a lot of my colleagues would say that they felt like they just had to type a lot more in Go, that it was much more explicit and much more verbose. So what I'm here to tell you today, though, is that Go has a couple of features that let you write Go in a way that can be just as expressive and powerful as something you might see there. And that we as Gophers can have nice things. We can have nice, easy-to-read APIs. We can have these really terse pieces of code that are still faithful to the values that have drawn us to Go in the first place. And in the process of that, I want to show you how subtly powerful some features of Go are if you think a little creatively about how to use them. And of course, in general, I'd like to encourage everyone to think creatively about how we can use Go in ways that that might be unexpected. And so all of this is based on a blog post that I wrote a couple months ago for Gopher Academy's Advent series. They do it every December. There's about 31 days of really fantastic content on Go, and if somehow you haven't encountered this series in the past, I really recommend going on to gopheracademy.com and checking out the last couple of years worth of posts, because there's some pretty great stuff in there. And so any of the substantive code that's in this presentation today is in that blog post, as well as a bit more discussion of what I'm going to be talking about. So I want to talk about how we can create DSLs with two tools for abstraction in Go that I think are somewhat underrated. And sort of shooting myself in the foot, the first of those are what we call type identities, which is actually something that you use all the time when writing Go. It's probably likely that you use it within the first 90 seconds of anything you do in Go. It's just binding a type to a name. So when you declare a struct, you're creating a type identity. But you can also create type identities where you create a new name for a known type. So here on this slide, I'm saying I have a type word of the day that under the hood is really just a string. So this unto itself isn't all that exciting. But as I suggested, this feature of the language has some power that you may or may not be using to its fullest potential. So you can take a type like a string, and if you create a new identity for it, like word of the day, you can create additional methods on that type and add behaviors. In this case, my word of the day has a method called exclaim, and when I call that method, it prints out the word of the day with a bunch of exclamation points. Not so exciting unto itself, but we'll get into some ways that we can make this more exciting. And you can create all kinds of syntactic sugar using this feature, and that's what helps you get at something like a DSL. You can find a little more detail about it in the Go spec, which is eminently readable. So on an atomic type like a string, this isn't all that interesting, but if you use it on a collection type like a slice or a map, you can start to get into some pretty interesting things using the methods that you can add to these types with type identities. So for this simple example, I'm going to say that I'm going to rename the string type host. It's going to represent a host name. And let's say I want a list of host names, so I'm going to call that a host list, which under the hood is just a slice of hosts, which in turn is just a slice of strings. Likewise, I'm going to create another type that I'm calling host set, and that is just a map of hosts to the empty interface. And so I'm going to create 3 methods on set, and so the host set under the hood is a map, but we're going to access it with set semantics. A set being a collection that is unordered, but contains no duplicates, and one of the things you might want to use it for is to quickly check whether a random host is contained in that set. So I've created a method add of my host set that under the hood just adds an entry to the map with an empty struct corresponding to the host that I pass in. Likewise, I can remove a host from my set, and under the hood that just deletes that key from the map. And then I also have a method called contains, which just gives me back a Boolean indicating whether the host that I've passed in is already contained in the set. Sorry. So none of these are terribly long pieces of code, but if you were to use a map, let's say to represent a set throughout your code, you would have to make sure that at every point you accessed your map intending to use it as a set, you were obeying the set semantics that you had in mind for it. Wrapping this up in a type identity is one way to create a mechanism to make sure that you're always respecting the semantics wherever you're using that set. And so here is a pretty simple illustration of it. I make a host set. Again, under the hood, that's just making a map. And then I'm adding a bunch of elements to it. I'm adding the host name golang.org. I'm adding google.com. I'm adding gopheracademy.org. And then I'm also removing google.com. Right under that, I just create a host list literal right here. It's the same host names that I just worked with. And I'm going to iterate over them, and I'm going to check if the set that I declared contains them. Lo and behold, they're all present except for the one that I explicitly removed. And so here this is just a simple map, but we've been able to create this encapsulation of the idea of a set using a type identity on top of it. So another feature that Go supports that is tremendously powerful, that again you probably use, but really can play a role in writing some nice declarative APIs, is higher order functions. Go lets you treat a function just like any other piece of data. You can pass it into another function. You can pass them around. And so we're going to look at higher order functions, which are essentially functions that operate on other functions. They can take a function as input, they can give a function as output, and do all sorts of things in between. And this particular one, I've created a method on the host list type that we created a couple of slides ago. Again, under the hood, that's just a slice of strings. And it has this method select. And I can pass in a function that takes one host parameter and returns a Boolean. And then we range over the elements of the host list. And if the function that's been passed in, when invoked on each of the elements in our host list, returns true, then we add that host to the output host list. Effectively, it scans the list and just returns anything that matches whatever criterion you've passed in. So the select method is a higher order method that operates on another function and lets you use that function to select items out from your host list. So just a quick illustration of that. I've created one of a predicate that I'm calling is.com. It just checks whether the host name ends in .com. And so here's our familiar list of names again. And here's our invocation, our host list. We're going to call the select method of our host list, passing in this is.com predicate. And here's our output. It left out golang.org, but showed us the elements that end in .com. And so you can see that this code right here, it ranges over the elements of the list and assembles a new list from them. But we've kind of swept all of the imperative details of that task under the rug of this declarative API. It's a list that consists of the elements of a different list that meet some condition. So you might think that passing in that this signature can get pretty gnarly pretty quickly, that we have this type. It's a function on a host that returns a bool. So we can use our type identities on function types as well. So I'm going to create a type called host filter that corresponds to just a function with that same signature. And then we can, just as before, the way we declared methods on our custom types, we can actually declare methods on a function type. We have functions that have functions. And so a pretty natural behavior to add to something like this filter, this predicate, is some ways to combine it and compose it with other predicates. So a host filter has a method called org, and you can pass another host filter into it, and then in turn you get still another host filter that consists of the logical disjunction of the two host filters you started with. This one returns true if either of those two host filters is true. And then similarly, we have one with and. It just does a logical and on the two filters. So at this point in the story, we hit on something of a wrinkle in this bill of goods that I'm selling you. Our function is.com matches the signature of a host filter, but as declared is not actually usable as a host filter where you can use these methods that we just declared on it. It's actually not enough for any variable to just implicitly match the underlying type of your type identity. It has to be explicitly declared as that type, and there are a couple of ways that you can get at that. One of those is this sort of unsavory construction that I've put here, where you declare a variable of the type of your type identity, in this case a host filter, and you assign to it, in this case, a function literal that matches the signature. Another option you have is to have a function that returns something of your custom type of a host filter, let's say, and then you can also do an explicit cast. But suppose you do have something like this right here, is.org, that is created as a valid host filter. You can create some other host filters like has go. This one just returns true if the host name has the word go in it. And is academy just returns true if the host name contains the word academy in it. And so here's our same familiar list of domains. And so we're going to do gonna compose these functions here in two different ways. We're gonna compose is.org with has go. So the condition here is, give me back the host name if it's a .org or if it contains the word go. Likewise, we have one, show me any domain name that has the word go in it and is also an academy. And again, we just run it real quick. And sure enough, Go sites, they all match. They all either are .orgs or contain the word Go. Likewise, Go for Academy is the only domain here that has the word Go and the word Academy. And again, you see here something that looks kind of like a declarative API taking shape. You're doing a couple of Boolean operations. You're ranging over some input, but you're really just describing the end result you want. You're describing a list that has selected the elements that match a particular criterion that you have assembled from other criteria. That I think if you look at a line of code like this, it's somewhat more clear and readable about what you intended from this than something that explicitly ranges over the list and checks each of the conditions and appends to the output set. Likewise, it's also, there's an opportunity to create new behaviors on the fly by combining these things. So some caveats with higher order functions in general. I think Go code tends to be really readable. The truly unreadable Go code that I've read has abused higher order functions and functions as variables. So use it with caution. Creating anonymous functions and function literals and passing them around is a really great way to make code that is hard to debug. And likewise, taking a function and passing it through too many levels of indirection also is going to break your ability to search through your code and figure out where things are happening. So be careful out there. So just to recap, we looked at type identities, which you can use to create some nice syntactic sugar. You can encapsulate certain concepts around new types that you create, even if they're materially not really different from any other type that exists. You can add methods to things to create additional semantics on existing types. So on collection types, you can have meaningful methods around how you access the data in that collection. With function types, you can create operations for composing them with other functions. This also works with channel types. There's some pretty interesting things you can do with that as well. And likewise, we looked at higher order functions as a way to compose bits of logic and behavior from other bits of logic and behavior. And we saw that as a way to sort of save some typing and also create some really descriptive code. So to kind of illustrate these concepts in action, we're going to create like a toy DSL around HTTP middle-ware, which is a great domain for this because anytime you've written anything that responds to HTTP in Go, you're generally re-implementing a lot of the same patterns. Maybe around logging, maybe around capturing metrics, maybe around authorization, authentication, all kinds of request filtering. And so this is a great candidate for something where you could just declaratively describe how you want your endpoints to behave rather than rehashing the same old imperative code. So we're going to look at a couple of different types. The first one already exists in the standard library. In the HTTP library, there's handler func, which is typically the function that actually responds to an HTTP request. It takes in the response writer and request object, and what happens in between is up to the implementer. And then we're going to add on two function types of our own. One that we're going to call middleware, which is a function that operates on some handler func and then gives us back another handler func. Could be the same one. It could be something that short circuits the handler func if certain conditions aren't met, or maybe it does some additional behavior that we'd like to have happen every time we respond to an HTTP request. Likewise, we're going to create a function type called a request filter, and that is just a function that takes a request as input and returns a Boolean that perhaps indicates whether we want to handle that request, whether we want to reject it, whether we want to route it to something. It's up to you. So here's a really simple implementation of a request filter. This is probably the longest block of code that I'm going to put up on the screen today, but it's not the most interesting. Essentially, this is a function that takes in a list of CIDR blocks, which look like this down here if you're not familiar. It's essentially a range of IP addresses. And it's going to return a request filter. It's going to enclose the CIDRs that we've passed in. And the request filter that it returns is going to be a function into which we pass an HTTP request. It's going to look at the remote address on that request, and if it matches the CIDRs that have been passed into our request filter builder here, then it is going to return true, and if not, it's going to return false. And we'll decide down the line what we want to do with that information. Some other possible request filters we might look at are this extremely stupid authentication method that I definitely haven't pushed into production anywhere, that just checks for whether a certain header is set to a certain value and flags it as true if the password matches and otherwise false. Another one just checks whether the specific HTTP method on the request matches an approved list. So maybe you only want to respond to GET requests or head requests, and this method here will let you will give you a filter to determine that. So request filter is great and all, but we want a way to create a middleware out of that, something that's actually going to be able to modify our HTTP handlers. So here's a function called allow, which does what it says. You pass in a request filter, and it returns a middleware. And this is where things start to get a little wonky. So this is a function that takes in a function and returns another function that takes a function as input and returns still another function. And so the next level of function in here, the middleware, has enclosed the request filter that we passed in, and it creates a middleware that I can pass a handler func into, and it's going to return a handler func that is going to check the request filter that I've given it on the HTTP request that comes into a handler, and if it passes, it's going to call the initial handler func that I passed in. Otherwise, it's going to return an HTTP 403. So note that allow, this outermost method here, function rather, returns a middleware, which is a function that operates on another function. It doesn't return the handler func itself. So here's just a super simple server that we're applying all of this machinery to. So we're using that method CIDR to create a request filter, and then we're passing that into allow. So CIDR here is going to return true whenever the request that's passed into it matches the CIDR block that we've passed in. In this case, localhost. And it's the middleware that we've created here is set up to allow anything that passes that filter. And we're in turn applying that middleware to a simple handler that just prints hello. So if you set this up and run it, and you'll find that if you hit this endpoint from localhost, you'll get back a nice hello response because you satisfy the CIDR condition. The allow middleware then allows the original handler to be invoked, and you get a hello response. If you hit this from any other IP address, you don't pass the request filter, and so the underlying handler func never gets invoked. Is everyone good with that so far? I jumped through a lot of levels of indirection against my own advice. All right. So we can also create more useful types of middleware, things that don't just filter out requests, but maybe do something useful like logging the request. And here logging is, as a middleware type, is a function that takes in a handler func and returns yet another handler func. And it returns a handler func that is going to print the time, the HTTP method, and the request URI before invoking the handler func that we passed in. And so all we have to do is just wrap it around the filtered endpoint that we already created, and lo and behold, we've added some pretty simple logging to that HTTP server without modifying the underlying handler function in any way. So we've hit a point where we need maybe a more powerful abstraction than what we have so far. We have, these filters which we can use to build middlewares, and we can compose all these middlewares on top of our endpoints, but we haven't even done anything all that interesting yet, and already we've ended up with a pretty gnarly piece of code. It's true that we haven't had to modify our underlying endpoint at all to add all these behaviors to it, but we've already made a pretty difficult to read and easy to get wrong invocation to build that. So it would be useful if we had, some other types, some other abstractions that we could use to set up how these endpoints are going to get built using our filters and our middleware. So we'll work off the assumption that we might want to apply multiple filters to a request. So we'll create a new type identity called filters, and all it is a slice of request filters. And filters has a method called combine that basically flattens all of the request filters in that list into one final filter that just returns true if all of the filters in that list are satisfied. Likewise, we're probably going to want to apply more than one type of middleware, so we'll create a type, and we'll call it stack, and that is just a slice of middlewares. And similar idea, it has a function called apply. You pass in an endpoint, and then it will just apply all the middlewares to that underlying handler in order, and then return the resulting handler func. So the result is your handler func with a whole bunch of middleware stacked on top of it. And now we needed something that we can use to pull it all together. So we've talked about having some filters and some middleware and an underlying handler func. So why not create a struct that we're just going to call endpoint? And it has member variables for each of these things. And endpoint is just going to have a method called build that's going to go through, and it's going to create one request filter out of all of the filters that we've passed in with allow semantics, and then it's going to call allow on the resulting filter. So we get one final middleware that is just going to allow any request that satisfies all of the filters that we've passed in. And from that, we have a handler func that we're going to call restricted. It's our initial handler func, just with all of the filters applied to it. And then on top of that, we're going to take any other middleware that we've applied, so logging, some other things that we'll see in a second, and we return that. And the result is a handler func that we can use anywhere else that we might, we can put it right on our server. And so this is starting to look like one of those DSLs that we saw earlier on. We used, some higher order functions, we used some type identities, and now this kind of gnarly invocation here is starting to look kind of readable. It lays out pretty clearly what all of the pieces are, and we have some nice readable code that explains in what order all of these things get applied. And just kind of as an illustration of the benefit we get from this, what we have now with this endpoint type is something that's more scalable than this nested invocation here. What we have is something where now I've just added some more. I've added 2 more filters, and I've added another bit of middleware. Now I've added something that's going to set a header on the response. I've added some really simple password authentication. I've added a filter that's going to cause my endpoint only to respond to HTTP GET requests. And it's pretty simple. I'm just adding 3 lines to the file. I'm not modifying the underlying handler func. I'm not adding to this nested nastiness. I'm just adding to this declaration here. So this wouldn't be that interesting if we couldn't also scale it to multiple endpoints on one server. So I'm going to create yet another type identity that I'm going to call roots. And it's just a map of strings to endpoints. And my roots type is going to have a method called serve. That's going to take as input an address to listen on, same as the the standard HTTP server method. And what I'm going to do is I'm just going to create a new serve mux, and then I'm going to range over the patterns and the endpoints in my roots map. And I'm going to, for each of the endpoints, I'm going to build it and turn it into an actual handler func. And then I'm going to route it to the pattern that it was mapped to into my roots type here. And then I'm just going to launch the server with, on the address that I specified with this serve mux that I just built. And so then that means that you can declare a whole bunch of endpoints on one server and the routes to get to them in what is basically just well, in this case it's a map. It's a map of structs. And if you look at this isn't really any worse than YAML. We have a pretty clean, pretty readable description of, okay, at the root /private, I have an endpoint that has as its underlying handler hello. It's only going to allow requests from localhost with the correct password. And of course, I'm going to log each one of those requests. Likewise, I'm going to have a test endpoint that doesn't have any access restrictions, but it's also going to have logging, and it's also going to set a header. And again, we can add to the complexity of this just by adding to the middleware stack, adding to the list of filters in allow. And one thing you'll notice here. So the Go language is doing some of the heavy lifting for us. So because I've declared this as a roots literal, that means that I don't have to specify. Well, here it's a string literal for the keys, but the values, the endpoint type is inferred. So I'm saved a little typing, a little verbosity that would make this a little less readable. Likewise, because I've called a list of request filters just filters, now I can create this filters literal here with kind of a sensical name to it. All of these types have been named in a way that doesn't cost any readability. If anything, adds to it. So yeah, I just discussed this. So note that we use the type identities for some cosmetics. It makes things look a little prettier and a little more readable, but it also in some ways marks what the semantic meaning of each of these elements is, and then we use the higher order functionality to be able to assemble methods that behave in ways that we define dynamically. Dynamically in the sense that we don't have to rewrite the method. This all still happens at compile time. We're not using any runtime magic or anything, but at the same time we've been able to specify some pretty complex behavior with some pretty simple code. So we created this whole API without doing any kind of reflection, not to denigrate it. I know we're about to hear about reflection. There's not a lot of magic here. We're using kind of well-known features of the language. We're keeping type safety. We're not doing anything terribly unsavory with this. We found that just by applying a few simple features of the language in a creative way, we've come up with code that is, as terse as anything we might see in Ruby or Python. And yeah, I mean, this all comes from language features that are straight out of the box. You don't have to generate any code, don't have to use any reflection, don't have to use any generics, nothing crazy. This is all pretty simple mainstream stuff. That's what I got. Thanks, everybody. Any questions?
I can give you the mic because we're recording.
I was just wondering if the slides would be available.
Yeah, sure. I'll put them up somewhere, and I'll drop a link in the page on Meetup.
Any other questions? Nope. All right. Thank you. Next talk is by Henry Clifford, right here. He's the CTO of a company called Live, and he's going to speak to us about parsing CSVs in Go. I don't know why, but you can ask him about that.
It's not personal. What was the password again? All things square. Cool. Cool. Firstly, thank you to Franklin for organizing this and to Squarespace for having us. My name is Henry Clifford, and I work for a company called Live. Essentially, it's a dynamic map of places, experiences around you. We've mapped out every bar, every restaurant, every music venue in New York. Can you hear me okay?
Because we're recording.
Okay. I guess the beer has to go. All right. Thanks. And to get all of this data, we use a combination of boots on the ground and machine learning. So anyway, that's my plug. I've been using Go in production for about 3 years. Really like it. Prior to that, Python, Clojure, normal stuff. All right, so I'm going to talk about CSVs and reflection. So that's a big old white. Why would you not want to do these things? Like, why are they bad? You know, reflection is slow, it's complicated. The bus factor for the CSV reflection code at Live is pretty goddamn low. You know, if anyone else wants to work with that, it's going to be really difficult. It's slow, comparatively speaking. So why would we want to do this? Why would we want to work with CSVs? Well, CSVs are everywhere. For better or worse, they're de facto data interchange format. DB2, if you're old enough to remember that exports CSVs. Postgres imports CSVs. If you're like me and you work with government data, you will be swimming in CSVs. So why reflection? Well, it's one of those kind of balancing acts. For us, the complexity is worth the trade-off of the non-negligible trade-off of the increase in complexity for, you know, being able to handle arbitrary input and output, which for marshaling and unmarshaling is something you're going to be doing a ton. Other areas it's nice for logging, debugging. You know, maybe performance isn't so sensitive in those areas, and you could use the expression. That's the goals for the talk. That's what we're going to do. So we can't talk about reflection without a quick primer on interfaces, which basically reflection lets us work with Golang's runtime type system. If you go into the Go internals, you'll find that the reflect library and the runtime library are actually pretty goddamn similar. Obviously it's Go, so a little repetition is better than dependency, but the two are pretty intrinsically linked. You know, my phone's going to go to sleep if I don't tell it to stop muting. Oh. So these two functions are kind of the entry points, reflect.typeof and reflect_value_of. Now, for those of you who don't know, an interface is a pair. It contains a pointer to the underlying value and some type information about the value you've got. And these pair of functions line up with getting this pair out of the interface. What does this look like in practicality? You're probably familiar with the JSON encoding package. Here we pass in an interface of arbitrary input, and then we use reflection to learn about this input and encode accordingly. Just got a demo here. I'm sure you've seen this code before. This is nothing special. But basically what we did was we passed in some arbitrary input, a structure, and then we used reflection to learn about the type, what fields were in there, and their types. You can see we used the JSON tag information from the type to construct the keys, and we used the field types to dictate how we marshaled them. Strings get quotes, numbers do not. Breathtaking. So we're going to build our own. We're going to build a marshal2 string, which is, CSVs are strings. And you'll notice that the function signature is very similar to the JSON marshal. We pass in this interface and we return our constructed output. And you'll see lines 10 and 11, that pair coming up, the reflect.value of and the reflect.type of. So what are those? And actually, before that, if you're observant, you'll notice we could have used a type switch here. Why didn't I? Well, great question. There's no reason to not. If this was your code, if this was your end goal, you'd be much better to just use a type switch and call it a day. Later on, we're going to build on this, which is why I am not. Just trust in me for now. So what is a reflect value and what is a reflect type? The value is not the actual value. It's an interface around it that lets us get information on it. Same thing for reflect type. It's not actually the type. It's not like string or int or pointer. It's a interface that lets us ask questions about it. How many fields does this type have? What are these struct tags? So on and so on. Reflect value lets us do things like ask how many items are in it. Or in the example of line 16, cast it to a string. Line 18, cast it to an integer. You get the idea. Kind. Kind is a type method that tells us what the underlying type is. I have more on this. Oh, I guess a demo would be. So for each of my inputs here, I've iterated through and marshaled it to a string. The strings got like that. The integers, we used the string convert package, and the booleans, ditto. So pretty vanilla. This is just an enumeration of reflect.kind. It's just an internal enum that tells you what the underlying type is. So like I said, reflect.type is not the type, but if you use the kind property, you can find out what it is. So these should look familiar. We have our compound types at the top, and the more vanilla ones as well. All good? Okay, onwards. Okay, so this is the internals of the reflect package. Here there be dragons. I literally copied and pasted out the code into the presentation. Don't take my word for it. You can go and look. And this is what the type of function does under the covers. You pass in an interface, and it gives you back a reflect.type. And to do that, it's using unsafe.pointer. If you're not familiar with unsafe.pointer, there's a reason it's called unsafe. Unsafe pointers allow you to defeat the Go type system by reading and writing arbitrary memory into structs. So what we've got here is two different structs. You can see type A and type B do not have the same fields. If you were to attempt a direct type conversion here, you would not be able to. The compiler wouldn't let you. However, with unsafe.pointer, we can take the memory from struct A and kind of just push it through, force it into B, and then this does actually work, bizarrely enough. We can see, boom, last name Henry. Magic. So why is this unsafe? If I add another property, let's say age, integer, and I run this, you'll see that I have some no so bueno data. That's because we're reading and writing arbitrary memory, and what we had to do, we had to fill B, and so we read all of A's memory, but then we just kept reading, and I don't know what else is in the memory. So whatever else was there provided us this lovely value. So if I go back now, this starts to make a little more sense. I said earlier that interfaces are made up of a pair. They're made up of a pointer to the underlying value and some type information. And what we've done here is we've taken the interface and turned it into this type empty interface. This is because they share the same memory layout. This is how Go internally stores interfaces. We have our pointer under Word, and we have our R type, which is a concrete implementation of the type interface. Type of simply gives us the .typ property, and you'll find that value of just gives us the word property. All good? Great. So, did that. I don't expect you to believe me. So I implemented one here without the reflect package. What we did here is we made a string Henry of type interface. We force it into type empty interface using unsafe.pointer again, and then we print some properties out. So basically, I would expect the underlying value to still be Henry. It's still the string Henry. I would expect the type to come back as, well, actually it's going to be the R type, which contains all of my other properties. So size, the amount of memory it takes up, hash, self-explanatory, kind, which should be a string, which I print out here. There's some other stuff like where does this live in memory, blah, 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 but that stuff's a little cryptic. And if I run this, you can see that's exactly what it is. You know, interfaces, reflection, not magic. This is what it's doing under the covers. All right. Did that, did that, did that. Did we do this? Did that, cool. All right, so the role of kind in the type is used to constrain the API, the reflect API. In our other examples, all the way back, we had these methods cast to int, cast to bool. Now, what happens if there isn't an integer? What happens if there isn't a bool? What happens if if my reflect.value, if I took this and I did, you know, this? Go uses kind under the covers to avoid you letting, sorry, it will panic if you do this. Let's just cut through that. Because we're reading and writing arbitrary memory, you remember I had my age as some really weird number when I was reading and writing arbitrary memory. So Go won't let you do this. It uses kind to enforce relative safety of the methods. Internally, when I cast to a bool, this is the bool method from back, this must be simply does a kind check. It looks at the internal kind property, asserts that it's a Boolean, and if it's not, it panics. And then you can see we're back to unsafe pointers. We're forcing arbitrary memory into type Boolean. So every kind has a corresponding reflection method. There's Boolean, there's string, there's integer, and then there's the corresponding, yeah, I'll come back to that. So with this one, I've started to extend. I'm using a compound type slice. And now here's where it starts to make sense to use reflection instead of a type switch. If I wanted to use a type switch for slices, I would have to declare every single slice that I might want to marshal. Instead here, I'm able to generically handle slices just by switching on the kind. So on 24, I ask the value how many elements are in it, and then I iterate through them using the .index API method to get the appropriate element. This will panic if the kind is not a slice. And then for each element, I actually recurse through and call marshal on it again. This is nice because this means that I can handle slices of slices or slices of strings of slices, or, you know, you get the idea. This is a, yeah, recursive. Nice little bit of debugging, and then strings. You can also do this for maps. The interface is pretty similar. I was going to live code it, but I'm not feeling brave. If I run this, cool. We can see my new type, which is a slice of strings, has successfully encoded. I iterated through each of my elements, and I marshaled them into strings, bundled them into an output, and then strings.join, you know, normal stuff. So I want to talk to you about marshaling structs as well, but I quickly want to recap exported and unexported. Something is exported if other packages can access it, and this is normally done by uppercasing it. Reflection can read unexported fields, but the question is, should you? When you JSON marshal a struct, it actually doesn't print out, it doesn't marshal the unexported fields. This to me kind of logically makes sense. Exporting is for moving things out of a package, and unexported things should not leave the package. Reflection cannot set unexported values. More on that. So here I have, here's my map example, by the way. Pretty simple stuff again. Reflect value map keys gets the keys of the map. It panics if the kind is not a map. And then we iterate through the keys, marshal those because we're being recursive, and then marshal the value because we're being recursive, and then bundle it out. But this is a little more interesting to me. This is reflect.struct. And now, with our other kinds, we were mostly looking at the value. But with struct, we mostly care about the type. That's because with slices and maps, the size is dictated at runtime. You know, you can append it or you can reslice it. But with structs, we define all of its properties at compile time. So we're going to be mostly looking at, you see on line 67, we're looking at the reflect type number of fields. How many fields did we declare for this struct? Then we're getting on line 70 or 71, again, we're getting a specific field for the struct instead of the slices where we were kind of iterating through the values elements. On line 73, there's a slight incantation for figuring out if a field has been exported or not. This one didn't really make sense to me, but there you go. And if I run this, cool. Here's my struct. I've turned my sister into a struct. You can see that name is exported, age was not. And when I passed that in and marshaled it, we skipped age and simply encoded her name. All good? Cool. Let's see where I am in my notes. Ooh, quite some way. Setting and addressability. Addressability is a whole talk in itself. Addressability is Go's ability to address a value. It's kind of the inner workings of how Go does memory management. I'm not going to talk about it because it's just too much. But in short, it means a consistent memory location accessible from everywhere. This means that you can rely on a value being in the same place in the memory all the time. The easiest example of this is a pointer. To recap, a pointer is a variable that contains a specific memory location. That means whatever's at that location has to stay at that location, otherwise pointers wouldn't work. If a pointer was pointing at code block memory block 30, and then whatever was in 30 kept changing, your pointers would change all over the place. So pointers consistently refer to this same piece of memory. There are some other types in Go that are also addressable, notably slice elements and arrays. Maps are not, weirdly enough, but interesting. So fields of a struct can be addressable, but only if the struct itself is addressable. And in plain English, that basically means you have a pointer to a struct, not just a struct. When you do JSON.unmarshal, you always pass in a pointer to a struct, not an actual struct. So, yeah. Cool. As mentioned earlier, to be settable, it also has to be exported. So here's an example of just going over addressability very quickly. I've provided some examples. We can see that a slice is not addressable, but a slice element is addressable. Pointers are not directly addressable, but the underlying value is, and a struct field is only addressable if it's exported. So here this is saying name is addressable, but age is not. Honestly, this stuff is easy just remembered or looked up. So here I've started to build out a basic CSV unmarshaler. So we start off with our famous pair at the top, reflect type and reflect value. We check that we have the correct kind. We resolve the underlying value. So I mentioned this earlier, pointer points to a consistent memory location. .lm resolves what is actually there. The pointer is actually very small. It just says go here. So lm gets the underlying value. And then we switch on the kind. This should start to look familiar. And then we set the value. Again, the reflect package uses kind internally to panic if you're not actually setting on a Boolean. So here I've provided, this is my mock CSV. It's a string that says true. And I'm unmarshalling into a pointer because I need it to be settable. So I pass in my pointer interface, I reflect type, I reflect value, and then I set it. And again, all the kinds have these corresponding methods. There's set int, there's set float, rah, and the internet's down. Just take my word for it. Okay, so to just recap on what I wanted to go through. Understand the relationship between reflection and interfaces. Reflection lets us poke into the interface pair and learn about the underlying value and the type. I've gone over the basics of the reflection API and how it uses kind to keep it safe, and we've kind of applied it to a real-world use case. I've actually packaged some of this up into a GitHub kind of library. If you're interested about reflection and a bit more surface area of the API, because there is quite a bit, you should check this out. I've done slightly more in-depth encoding and decoding methods. Any questions? Cool. That's it. I think I'm a little early, so thank you very much.
Thank you, everybody, for coming. Just so you know, I work here at Squarespace. That's why I did the first meetup here at Squarespace. If any of your companies is interested in hosting this meetup, please reach out. As I mentioned before, if anybody knows speakers, please reach out as well. We do use Go here at Squarespace, from keeping zookeepers in sync across data centers all the way to distributing IP table rules across all the edge nodes in production to protect us against DDoS attacks, everything written in Go. I just need to convince those engineers to come speak here. So hopefully one of these days. And I'm gonna try to make this a monthly thing as long as we have enough speakers, just so you know. There's more food, there's more beer, and you're welcome to stay. Thank you.